For decades, cosmology has had a clear expectation. Small galaxies form first. Large structures take time. But new observations from the James Webb Space Telescope are starting to complicate that picture. Astronomers are now seeing signs of large-scale structure assembling much earlier than many models predicted. Not because the universe suddenly changed, but because our measurements are getting sharper. This isn't a crisis for cosmology, it's a constraint. Let's break down what's being seen, why it matters, and what it actually tells us about the early universe. What you're seeing here is not just a collection of early galaxies. The infrared points mark individual galaxies detected by Webb. But the faint blue glow is something else entirely. That's hot gas seen in X-rays, trapped inside a shared gravitational well. And that matters, because gas like this only appears once enough mass has already come together. It's a sign that large-scale structure is starting to form, earlier than many models predicted. Let's slow this down and be precise about what we're actually looking at. The points of light in this image come from infrared observations by the James Webb Space Telescope. Each one is an individual galaxy forming stars in the early universe. On their own, early galaxies are not especially surprising. Models have allowed for that for years. What changes the picture is the faint diffuse blue emission spread across the same region. That signal comes from X-ray observations by the Chandra X-ray Observatory. It's hot gas, heated to millions of degrees, and confined within a shared gravitational potential. And that detail matters. Gas like this doesn't appear simply because galaxies exist. It requires a substantial amount of mass already assembled, enough to compress, heat, and retain gas on scales larger than any single galaxy. In other words, this isn't just early star formation. It's the early organization of matter into what astronomers call a protocluster. According to many structure formation models, assembling systems like this should take time, hundreds of millions of years of gradual growth, mergers, and accretion. Seeing both galaxies and hot intracluster gas together suggests that this process may have started earlier or proceeded more efficiently than many models predicted. This doesn't mean the models are broken. It means the observations are beginning to place tighter constraints on how fast a large-scale structure can form in the early universe. And that's the real significance of this image. To understand why this matters, you have to compare it to what our models actually predict. In standard cosmology, structure forms hierarchically. Small density fluctuations collapse first. Those grow into galaxies. Galaxies then assemble into groups, and only later into clusters. That process is not instantaneous. It depends on how quickly matter can fall together under gravity, how fast gas can heat up, and how efficiently it can remain bound as structures grow. Most models place the appearance of hot intra-cluster gas well after the first galaxies form. It's something expected to emerge gradually, as mass builds up over time. What these observations suggest is not that the sequence is wrong, but that the timeline may be tighter than assumed. That large amount of mass may have assembled earlier, or collapsed more efficiently than many simulations predicted. This is a timing problem, not a contradiction. And timing problems are exactly how observations refine models. So what could explain this? One possibility is that the earliest regions of the universe were simply more efficient at collapsing than average. Rare, high-density regions can form structures earlier than most simulations focus on. Another factor is observational bias. Deep surveys like JADES are designed to find the earliest and most extreme examples first. Seeing an early protocluster doesn't mean they were common, only that they were possible. There's also uncertainty in how we model the first billion years. At those times, small changes in assumptions can lead to very different outcomes. What matters is that this is now testable. As JWST and Chandra continue to observe, and as more early structures are found, these timelines will either hold up or need refinement. So here's the real question. Are we seeing the rarest early structures first, or are our models underestimating how quickly matter can organize in the young universe? If you want to follow how that question gets answered, subscribe. And let me know in the comments what you think this tension really means.